Hello everyone! In this control engineering, control theory, and process control tutorial, we explain how to develop a dynamical model of a tank or a reservoir filled with the liquid and how to simulate such a model in Python. This is a classical problem for understanding the dynamics of fluids and process control systems. More precisely, by watching this video tutorial, you will learn how to develop a nonlinear differential equation describing the dynamics of the system. Furthermore, you will learn how to write a Python code that simulates this differential equation, and by the end of this video tutorial, you will be able to generate these nice graphs. The first graph shows the input flow to the tank, and the second graph shows the simulated water height or the fluid height in the tank. A link to this code will be provided in the description below this video. Okay, let's start with the problem formulation. We consider a tank with a cross-section area of A filled with an incompressible fluid. The fluid level at the time instant t is h. The input volumetric flow rate to the tank is denoted by QIN, where this IN stands for the input. The output volumetric flow rate of the tank is denoted by Qout. We assume that the output flow rate is passive. That is, we assume that this output flow rate Qout is not actively controlled. We assume that the cross-section area of this hole is much smaller than the cross-section area A of the tank. Also, we assume that we can control the input flow rate QIN. Our goal is, number one, to derive a differential equation describing the change of the fluid level h as the function of time and as the function of QIN. Then, for a given initial fluid level h of 0 and for a given time series of QIN, we want to numerically solve and simulate the solution of the derived differential equation in Python. Let's start with the solution. Our first goal is to derive the differential equation describing the dynamics of this system. On the left side over here, you can see the fluid level at the time instant t. The fluid level is denoted by h. Then, after some infinitesimally small amount of time, denoted by dt, the fluid level will be over here. This purple area over here is the fluid level change. During the infinitesimally small amount of time dt, the fluid level went from h to h plus dh. That is, it went from here to here. The rate of change of the fluid volume during this time instant is dh multiplying a. This is actually the volume whose cross-section is given over here. And since we're looking into the rate of change, we need to divide this by dt. This is equal to dh over dt multiplying a. Now, what is dh over dt? Obviously, this is a velocity. This is actually an instantaneous velocity of the fluid during this time interval, and we can write this is equal to v multiplying a. And this actually has a unit of the flow rate. Better to say the unit of volumetric flow. Let us make a small digression. In the most general case of the fluid flow through a pipe, and in the ideal case, the volumetric flow through this pipe is given as velocity of the fluid passing through this cross-section multiplying the area of the cross-section. And by comparing this general formula for the flow rate and by comparing this formula, we can see that from the mathematical perspective, these formulas are actually identical. To summarize, we learned that this term over here is actually the flow rate. This flow rate is a difference between the flow rate coming in, that is the difference between Q in, and the flow rate coming out, that is Q out. Consequently, we can write dH over dt multiplying A is equal to Q in minus Q out. Here, for clarity, I've wrote the formula once more. On the other hand, in our previous tutorial, we explained and derived the formula for the output flow rate. The output flow rate is equal to CD, where CD is the discharge coefficient, multiplying square root of 2g, where g is the gravitational acceleration constant, and multiplying the square root of h, where h again is the level represented over here. Next, for clarity and simplicity, CD multiplying square root of 2g will be denoted by C. Consequently, Q out is C multiplying square root of h. If we now substitute this equation in this equation, we obtain that dH over dt multiplying A is equal to Q input minus C square root of h. We can divide this equation by the cross-section area A. Consequently, we obtain dH over dt is equal to 1 over A Q input minus C over A multiplying square root of h. And this is the final form of the differential equation describing the dynamics of this system. Here, several things should be observed. First of all, this is a nonlinear ODE, where ODE stands for ordinary differential equation. This equation is nonlinear because of this nonlinear term over here. Then, for a given h of 0, that is, for a given initial level h, and for a given q input that's a function of time, we can numerically solve this equation to compute h as a function of time. In the sequel, we explain how to numerically solve this equation for an arbitrary input flow rate. Here's the code I wrote. This code contains a very detailed comments explaining every line. I will provide a link to this code in the description below. In the sequel, I will write this code from scratch and I will explain every line of this code. The first step is to import the necessary libraries. First of all, we will import the NumPy library. Then from scipy.integrate, we will import the ODE int solver. This is a solver for differential equations. And finally, we will import the pyplot module, such that we can plot graphs. Next, we need to define the model parameters. The first model parameter is the cross-section area A, and the second model parameter is this constant C. Let's do that. First, let's define A. Here, I will simply assume that the cross-section area is equal to pi. That is, I assume that the radius of my tank is 1. That is, I'm assuming that my tank is cylindrical and that the radius is equal to 1. Then let's define the C constant. I will assume a CD, that is the discharge coefficient of 0.6, and over here I will define the term square root of G multiplying 2. 2 multiplying 9.81. Okay. Next, we need to define the time interval and time array for simulating the dynamics. Over here, I will assume start time to be 0, end time to be 5 seconds, and in between, I will assume 1000 time steps. Next, we need to define the time array and the input flow rate. Here's how I define the time array for simulating my dynamics. I'm using the function numpy.linspace. I specify the start time, I specify the end time, and I specify the number of time steps. Let's see this vector, or better to say this array. Here it is. I'm starting from 0, and the end time is 5, and in between I will have 1000 time steps, or better to say 1001 time steps or time samples, since we start from 0 over here. Next, we need to define the input flow array. We need to make sure that the input flow array is positive. Here's how I specify QIN. It's simply a harmonic function, 3 times sine, simulation time, plus 3 times cosine, simulation time. Over here, I'm also specifying another version of Q input. This is for simulating the initial state response when the input is equal to 0. We will later on uncomment this line in the second simulation run. And let's plot over here our input. Here it is. You can also see it over here. Looks very nice. So this will be the input flow rate to our system. Next, we need to define the right-hand side of our differential equation. That is, we need to write a function that will evaluate the right-hand side of our differential equation for the given h. In my case, h is denoted by x for given time, for given array of time points, for given parameters a, p, c, p, and for the given input array. I will explain this function thoroughly. First, let us briefly revise our differential equation. Our differential equation has this form: dh over dt is equal to 1 over a multiplying qin minus c over a multiplying square root of h. To avoid any confusion, I will simply rewrite this function in terms of x. That is, I will substitute h by x. Consequently, the function will look like this: dx over dt is equal to 1 over a multiplying q input minus c over a multiplying square root of x. This function defines the right-hand side of this equation. Also, it evaluates the right-hand side of this equation for given a, for given c, for given x, for given time, and for the interpolated value of qin. Namely, the standard ordinary differential solver in SciPy library is not able to solve this differential equation by just specifying the time array of qin. We need to use a trick. We need to actually interpolate qin. And that's exactly what's happening over here. Time points and input array define the time series of our input, that is, of our qin. To explain this, you can consider this graph, and this is our q input. This is time, and this will be q input. And that's precisely the graph that you can see over here. What will happen over here? Namely, this solver will evaluate the values of qin for certain points. However, we cannot precisely define and specify the equidistant points in time. Consequently, we will need to interpolate between the values. The set of points, let's use different color, for example. The set of point denoted by this color is something that we provide to the solver. Here it is. And over here, we will actually interpolate the values for different times, since the solver might require the value of QN for this time. Consequently, we will be using this point over here and this point over here to interpolate the value. And that's precisely what's happening over here. This input Q then represents this term over here. We are just interpolating. Then over here, we are simply computing dx over dt, 1 over a is denoted by AP, and let's change it over here such that you avoid confusion. Here you will have AP, here you have CP, and here you will have AP. And that's precisely what's written over here. Here, the user can specify the arbitrary values of the parameters AP and CP, and that's all. Over here, we have a safeguard. Namely, if x is smaller than 0, we will set the derivative to be equal to 0. X smaller than 0 means negative liquid level. This is not physically possible, and we somehow have to constrain our solver. The easiest way to do that is just simply to set dx dt to 0 if everything is empty. This might not be mathematically 100% correct. However, we don't expect in finite time that the tank will drain. And finally, this function returns dx over dt. After defining the function that returns the right-hand side of our differential equation, we are ready to define the initial state. The initial state is 1, and the initial state is the initial level x of h of water in our tank. And over here, that is, in this code line, we actually solve the differential equation. We call the function ODE int. We specify the name of our function defining the right-hand side of the differential equation. We specify the initial condition. We specify the array defining the simulation time. And we specify the arguments of this function. And you can see simulation time corresponds to time points, A corresponds to AP, C corresponds to CP, and input array corresponds to QIN. Notice that AC, QIN, and simulation time are actually defined over here at the top of our code. And that's it. Let's run this code and let's analyze the result. Here it is. Let's see the output of this function. It's the solution state. Here it is. And the entries of this array represent the level h at different time steps. And finally, let's plot the result. Here it is. This function shows the level h as a function of time. We can see that initially level is 1, then it goes up since the flow goes up, then it goes down since the flow goes down, then again it goes up, down, and again it goes up because the input flow rate goes up. Next, let's double check and verify our implementation by computing the initial state response. The initial state response is the response of the system when we only have the initial height and we don't have the input flow rate. Over here, I will simply comment this line and I will define Q input to be 0. And let's simulate the system once more. And let's see the result. And here it is. Here is the simulated height or the level h when the input is 0. We start from 1, and since we have the output flow, we can see that slowly over time, the tank will drain out. And that's it. Okay, that's all for today. I hope that you like this video. If you like the videos I'm creating, please press the like and subscribe buttons. Thanks a lot and have a nice day.